On July 22, 2026, a regional transmission line outage struck Northern Virginia, sending a severe shock through the PJM interconnection. That localized fault triggered a cascading reaction. To protect their internal operations, multiple data centers in the area automatically decoupled from the utility grid and transferred to their own backup power systems. Modern hyperscale AI facilities possess the electrical footprint of small cities, concentrated into just a few square miles of high-density infrastructure. This incident report shows the immediate consequence. When those facilities switched over, more than 3 gigawatts of electrical demand vanished from the grid almost instantaneously. Stripping away that much load in a fraction of a second created a massive geographic voltage and frequency disturbance. The interconnected system struggled for roughly 10 minutes before it finally stabilized. This close call exposes a critical vulnerability in how we plan our power systems. Grid stability has historically focused on the loss of generation, but this event proves it is increasingly a load-side problem. We are transitioning from a grid anchored by the slow, mechanical inertia of spinning turbines to one dominated by the subcycle switching speeds of power electronics. The mathematical models and simulation techniques utilities have relied on for decades lack the fidelity to predict these high-speed interactions. To prevent future multi-gigawatt instability, the industry has to move beyond pure software simulation and begin validating equipment using physical, hardware-in-the-loop testing. Historically, grid protection has centered on under-frequency events. The primary fear was a major power plant suddenly failing. When generation drops, frequency drops with it, and the system sheds load to prevent a blackout. Massive electronic loads invert that equation. When 3 gigawatts of demand vanish in milliseconds, the grid is suddenly flooded with excess generation. This creates a severe spike in frequency that slow, mechanical generator governors have to furiously throttle back. The disturbance doesn't originate from a single point like a failing turbine, but from a decentralized network of facilities, causing the transient to propagate rapidly across the entire interconnected system. Generators are then forced to respond to violent, sub-second fluctuations that their physical hardware was never designed to track. The scale of modern computing means the sudden disconnection of these facilities hits the grid with the exact same severity as a nuclear power plant tripping offline. This comparison table outlines the incompatible control objectives driving the two sides of the meter. For a conventional grid, the primary objective is saving the utility. Tripping a generator offline is an acceptable way to isolate a fault. Because it relies on physical governors, this protection operates mechanically, taking hundreds of milliseconds to several seconds to react. An AI data center prioritizes continuous computing. Any interruption to the IT load is entirely unacceptable. To ensure that continuity, their protection relies on battery energy storage and uninterrupted power supplies, acting on a subcycle millisecond timeline. The result is a massive speed gap. The moment a grid disturbance is detected, the data center completely isolates itself to protect its internal silicon long before the utility's mechanical systems even register the event. The two systems violently decouple, leaving the slower utility grid to absorb the resulting power oscillations. The grid's fastest automated responses are simply orders of magnitude slower than the electronic loads they are attempting to stabilize. Currently, developers rely heavily on interconnection studies to clear these projects. But clearing the software simulation does not guarantee site-level stability in the physical world. The industry recently transitioned from positive sequence models to electromagnetic transient, or EMT, simulation for inverter-based resources. Yet EMT remains a software-only view. The mathematical model can only represent what the developer knows about the equipment, completely missing the proprietary black box logic embedded deep inside the manufacturer's actual firmware. We have to take the next step, moving from software approximations to real-time simulation and hardware-in-the-loop testing. Physical power electronics hardware regularly behaves much differently during extreme grid transients than their idealized mathematical models would predict. Fast control interactions, hard limits, and exact sequencing are only truly executed by the controller's compiled code. Software models tell us how an engineer expects a system to behave, but only physical hardware testing proves how it will actually react under stress. The solution is closed-loop testing, wiring physical OEM controllers into a real-time digital simulator before grid connection. This lets engineers evaluate system-level interactions, mapping exactly how energy management systems, battery storage, generators, and relays communicate. Developers observe precisely how energy loads buffer against the grid, and plant-level controllers react to faults. The highest levels of the industry are already forcing this methodological change. NVIDIA's updated guidelines for battery energy storage systems now explicitly demand physical hardware test evidence, deprecating reliance on simple model validation. Their qualification process requires strict physical testing for dynamic response, energy load buffering, and high and low voltage ride-through capabilities. They also make it clear that individual equipment passing a bench test does not guarantee the stability of the entire site once integrated. The Northern Virginia event sends a clear warning. The modern grid now responds directly to the subcycle behaviors of massive power electronic loads. As the system becomes entirely load-centric, our validation processes have to leave the pure software domain to match physical reality.